Hello, and thank you for being here. I want to talk to you today about a new elephant that has just entered the chat room. But first, we need to talk about the first elephant. The first elephant is why teach math? I have been teaching math for a while now, and I have been asked this question many times. My very first answer to this has always been quite selfish. Why teach math? Because I like it. I like math and I like teaching it. Then I get more pragmatic because they pay me to do it, and because it's perhaps the only thing I know how to do well. But the elephant still remains in the room. And it often transforms into the student question of why do I have to learn math? And there we have some stock answers always. Because it's useful, because it's good for you, because it teaches you how to think. And here's another one, because math is beautiful. And yet another one. You learn math and we teach math because it's a human endeavor and learning it helps you, me, us, connect with our common human heritage. Now all these have a bit of truth to them, but we all know that they are not always enough to convince students. They were not even enough to convince me fully, honestly. But I did not know what to do with that until I learned about Bloom's taxonomy. Bloom's taxonomy is a classification of types of educational tasks and objectives. Educators use it to evaluate the learning tasks they design to achieve certain educational goals. The original taxonomy dates back to the 1950s, when a committee convened to develop language and models to help educators design and improve curricula and assessment tasks. The final classification that became known as Bloom's taxonomy comes from the Taxonomy of Educational Objectives, the Cognitive Domain, published in 1956. Then later, early 2000s, Anderson and Krathwohl completed a systematic revision of the taxonomy, replacing nouns with verbs to describe the 6 levels. As you can see on the left-hand side, the triangle has only nouns for different levels. As you go higher up, evaluation is the highest level. And on the right-hand side, you see the new taxonomy, which uses instead verbs, remembering, understanding, applying. And also you can see that the top 2 levels have been switched. Evaluation becomes level 5, while creation, synthesis becomes level 6. Now, I'd love to dig into Bloom's taxonomy for mathematics education for you, but we do not have the time today. If you are curious, I did write a couple articles about the topic, and I will list them in the references. But for the purposes of this talk, let it suffice to say that when I first learned about Bloom's taxonomy, I was floored. I felt forced to think more carefully about the types of assessment tasks I was using in my own teaching, and I realized that teaching math to encourage the types of thinking that could rise to the higher levels of Bloom's taxonomy was quite a challenge. Along the way, I began to think more intentionally about what makes a good homework problem and what makes a good test problem. Now here's a good possible candidate from calculus. It's an optimization problem, quite a standard one, and I kind of like it. Similar problems show up in most calculus texts, and this is an exercise I took from Rogowski. Students need to think about what the problem is asking, how to model the situation, what to optimize, and so on. You could say that it involves so much thinking. But wait, let's look at a few pages earlier in the book. What do we see? Here is a solved problem from the same chapter. Almost the same problem shows up with a figure that would be almost the same for our hard problem. But of course, you say textbooks are for teaching and learning, so solved examples will be there for sure. So then I give you a neat problem from AP Calculus exams. Now, I haven't taken AP Calculus courses or classes myself, as I did not grow up here, but when I first saw the AP Calculus exam questions, some of them, for example, this one, which was in 2010, this is an AP Calculus AB exam problem, free response problem, I liked it a lot. I think this question brings together a whole lot of mathematical ideas that the student is supposed to engage with in order to solve it. But wait, let's look back a year. Here's a problem, similar type like a free response question from the 2009 AP Calculus AB exam. Let's ask productive teacherly questions like, what do you notice and what do you wonder? Well, I noticed that if I have seen this 2009 problem before, the 2010 problem will be quite doable. And I wonder, is our job as math instructors only to train students to be able to solve problems they have seen before? Let me say this as a factual, assertive statement. Our job is to train students to solve problems they have seen before. How do you like that job description? Well, I don't. I don't like that job description at all. This is a moment of crisis, and this crisis is captured for me best by John Steinbeck, who writes, "The lies we tell about our duty and our purposes, the meaningless words of science and philosophy, are walls that topple before a bewildered little why." But a lie? You might say maybe that's a little too strong. How about calling it a myth? Here's an article I came across many years ago while I was ruminating on these very questions. Peddling the Myth, Why Do We Teach Mathematics by Paul Andrews, who writes in his abstract, the continued tradition of justifying mathematics on the basis of its usefulness is a stumbling block to mathematics education. Tasks that teachers perceive to be embedded in some form of real-world reality trivialize mathematics, patronize children with their banality, and undermine children's natural inquisitiveness. Mathematics teaching needs to focus on mathematics for what it is and not on its applications. Now, Andrews' article is really good, and it was great for me to read at the time, and I fully recommend it. But for a more comprehensive answer to the why teach math question, I needed to look further, and it was Paul Ernest whose writing came to the rescue for me. In his article, Why Teach Mathematics, Ernest listed 4 good reasons for why we should teach mathematics. To reproduce mathematical skill and knowledge-based capability, to develop creative capabilities in mathematics, to develop empowering mathematical capabilities and a critical appreciation of the social applications and uses of mathematics, to develop an inner appreciation of mathematics, its ideas, big ideas, and nature. When I read this article, which was more than half a decade after Ernest wrote it, by the way, I began to feel like I was no longer drowning. At that time, I decided to see what math education researchers thought about the same question, why teach math? Together with a few students, I began a project on the purposes of mathematics education. We dug deep into the first 2 volumes of an esteemed math ed research journal, Educational Studies in Mathematics, to see what we could find. Through computational methods for text analysis that were slowly becoming more and more popular at the time, we were able to isolate 5 general goals for mathematics education. Math is taught because 1. It is elegant and beautiful. This is, of course, the first reason that most mathematicians will come up with. Math is taught also because it provides students a rigorous way of thinking, allowing for systematic and logical thinking whenever they can need that kind of thinking and solve problems. It provides students an intuitive way of thinking, encouraging heuristic thinking and creative problem solving. Mathematics is also useful to know, right? Some types of mathematics shows up in daily life, and this is, of course, branches into quantitative literacy, which takes on a life of its own. But mathematics is also useful to society in its scientific and advanced applications. Now, at that time, I was quite satisfied by this five cluster categorization of mathematical education goals. I felt like I knew how to handle that first elephant about why teaching math, why I was teaching mathematics, and from that time on, my goal would be basically to figure out how to do this job well. Then along came a new elephant. Okay, this is the new elephant entering the chat room. The new elephant I'm talking about here is actually generative AI, artificial intelligence, in the form of ChatGPT. The images you see here basically represent how I think of ChatGPT in my mind. It's a young and keen robot mind capable of doing an immense amount of stuff. So ChatGPT burst onto the scene in November 2022, and already in December of that year, people were predicting the end of the world, or at least the end of the academic essay. We math instructors might have felt a bit more immune, at least for a bit, because as I wrote in January 2023, the large language model ChatGPT was based on could not yet solve some very basic math problems. But as I said, it is young and keen and it learns really fast. Today, ChatGPT can do a whole lot more. In particular, it can solve many more standard math problems through a Wolfram plugin. It can write Python code and produce functional LaTeX code. It can also create striking visuals, interpret images, and decipher human handwritten math. It can also refer to real-time information via its integration with the browser Bing. Now, before moving on, I should note that in the rest of this talk, I will likely use the name ChatGPT, like many folks use the words Kleenex and Coke, which are the specific names for specific brands, but we use them usually to stand for a whole family of products marketed by a wide range of commercial entities. So when I say ChatGPT, you can also include all its siblings there, like Claude, Perplexity, AI, Genesis, and so on. So ChatGPT is here and is ready to help. Or is it? I have written elsewhere my thoughts on the many ethical considerations about generative AI for the mathematics classroom. Once again, the references will include a link to this article. But ChatGPT is not the only artificial intelligence of interest to mathematics instructors and mathematicians. The legacy of the 1976 computer proof of the four-color theorem lives on, and with a vengeance. today. Today, there is a lot of work on artificial intelligence systems that can support mathematical reasoning activities of human mathematicians and perhaps even take over as needed when things get too complex. For a review of where things stand these days with respect to this AI for mathematical reasoning stuff, you can check out the recent issue of the Bulletin of the American Mathematical Society. In particular, this is volume 61, issue 2, available online freely, as well as the recent publication of the United States National Academies titled Artificial Intelligence to Assist Mathematical Reasoning, also available online for free. There is even a recent call for grant applications through the NSF in the US on this very topic. But all this might not be immediately relevant to folks teaching math unless you are teaching a proofs-based class, in which case there's some pedagogical argument to be made that theorem provers might be helpful. Again, I'll include a reference below on that for those interested. But mainly, let us limit ourselves to generative AI based on large language models for now. Here, I want to channel Sasha Sidorkin. Sidorkin is not a math instructor, but I think his words on AI and education are quite relevant to us too. I am struck by the immensity of the challenge before us, he writes. It is not just about adapting to a new tool. It is about redefining the very foundations of how we teach and learn. It is about finding a way to harness the power of AI without sacrificing the soul of education. This is a journey that will require bold experimentation, deep collaboration, and a willingness to embrace the unknown. But it is a journey we must undertake, for the stakes are too high to ignore. The future of education hangs in the balance, and it is up to us to shape it with wisdom, courage, and a steadfast commitment to the human experience of learning. I must agree. To recap, why do we need to teach math now? Has anything changed? What has changed? I'd say that math has not changed. It is still beautiful and elegant. It still can provide students a rigorous way of thinking and an intuitive way of thinking. It is still useful to know some math in life, and it is useful to society for scientific and other advanced applications. But why should we teach math at this point in time? As the math we teach at school and the math mathematicians do in their practice become more and more accessible to artificial intelligence, this becomes a valid question. Why should human children need to learn math if soon one day machines will do it for them? First off, many folks will say that that day is not here yet, but we should probably not put all our eggs on that yet basket. Even if or when a time comes where machines can design and program themselves and solve many of our mathematical problems much faster than we can on our own, there should be room for mathematics in a good education. So here is my updated answer to why we should still teach math. And yes, still, and if not forever, at least for the foreseeable future. Mathematics, asking questions, solving problems, trying to understand big pictures, is still a human endeavor. And we build on that humanity to make sure our 5 goals are still a part of the mission of mathematics education. This requires us to add to our goals, if we have not already done so, attending to the humanity of our students. This is where I refer you to texts like Rehumanizing Mathematics and to outlets like the Journal of Humanistic Mathematics. So in short, we cherish the humanity of mathematics, all the while benefiting from machines that can help us solve harder and harder problems. We cherish its beauty and elegance, where truth of a statement is never the only value worth seeking. We build on its capacity to teach students to think systematically and creatively. We educate quantitatively literate future citizens of the world who can comprehend quantitative information and relationships whenever they come across them in their daily lives and careers. We support and train tomorrow's scientists and researchers who will build upon today's knowledge to reach further heights. And all throughout, we cherish once more the humanity of our mathematics and, of course, of our students. Thank you for viewing this presentation. Before I close off, I should mention this article by Professor Lisa Dara, which I read quite a few months ago. Professor Dara makes many incisive observations in this piece. I did not realize her title had made such an impression on me until I submitted my talk proposal for this talk, and then said to myself, wait, I think I have recently read an article with the elephant in the room analogy. So here's the credit I need to give, credit where it is due. I still like the title I gave to this talk, but it is not totally original to me. What do they say? Nothing new under the sun. Imitation is the highest form of flattery or something like that. Thanks again for listening. I hope you found some of this of interest.